For 10.1 day 1, we're going to do exactly what we have been doing for the last few days. And now we're really going to get into some of those nitty-gritty rules. So the first thing that we're going to do is, as always, list our perfect squares. We're going to go 1 squared to 16 squared here. So that's 1, 4, 9, 16, 25, 36, 49, and 64. That brings me up to 8 squared. 9 squared is 81, 100, 121, 144, 169, 196, and then these two big ones, 225 and 256, rounds out our count. So that's 1 squared through 16 squared are perfect squares. Now, we're going to add in some rules for simplifying our radical expressions. 3 rules that we're going to live by for this unit. The first rule that we've already kind of talked about is that a radical expression is simplified when there are no perfect square factors left in the radicand. That's our first rule. And then our second rule, which is probably a new one, is that the radicand itself, which if we remind ourselves the radicand is the number inside the square root, it cannot be a fraction. And then to kind of go off of that rule, a very similar rule is that there cannot be, or there are no radicals in the denominator of a fraction. There can be as many radicals as we want in the numerator or the top of a fraction, but we cannot leave radicals in the bottom of fractions. Those are our 3 rules that we're going to follow. So let's take a look at identifying unsimplified expressions. I'm going to go through each of these. We're going to figure out if they are simplified or not. For this first one, the square root of 18 is not simplified because I can take out of 18 9 and 2. 9 is a perfect square. It should actually be simplified to the 3 square root 2. Letter B is simplified. That one looks good. It follows all 3 rules. Letter C is not simplified because I can take out of 36 a 16 times 2, where 16 is my perfect square. We're going to move that out of my square root. It's going to become a 4. The 4 multiplies to the 5, so the simplified version should be 20 square root 2. Letter D is also not simplified. We haven't really gone over how to simplify these ones yet, but this one is not simplified because the radicand is a fraction. And that breaks our second rule in that box. Letter E looks good to me. And then once again, letter F breaks that third rule this time. There is a radical in the denominator, so that will not work. And the last one, letter G, is also not simplified. 100 is a perfect square, so we know that we can simplify that to just 10. All right, so with those rules in mind, we're going to go ahead and do some simplifying of some radicals. We use this multiplication property. We've talked about it before. It's what allows me to take a number and break it down into the product of its perfect squares. So we, once again, are going to be determining the greatest perfect square factor that the radicand is divisible by. So for 36, 36 already is a perfect square. So I know that if it is a perfect square, I'm just going to square root it and make it into a 6. That radical goes away. 50 is not a perfect square, so I'm going to use that multiplication property and break it into the largest perfect square that I know goes into it is a 25. To get that 25 to the outside, I'm going to square root it to be 5. And then I have a 2 left over on the inside. Letter C, I'm going to leave that 2 out in the front, and I know that 45 can break down into 9 and 5. That's its largest perfect square factor. 9 is the perfect square. I square root that. It goes to the front as a 3, but there's already a 2 here, so I want negative 2 times 3, which gets me negative 6, and then I have negative 6 radical 5. And then the last one here, letter D, I'm looking for the largest perfect square that goes into 42. I remember I have my list when it comes to these big numbers, and I should be starting at about 225. That's the next largest number after 242. So I'm going to go up my list, 196, 169, 144, until I get to 121, which does end up dividing into 242 evenly. That's 121 times 2. 121 is the perfect square, so we're going to go ahead and square root 121 to get to 11. 5 times 11, 55, radical 2. So that's for our numbers, just our plain old numbers. In example 3, now we're going to make it a little bit more complicated. We're going to have to do a little bit of multiplying first. So in letter A, I can multiply these two radicals together. The square root of 8 times the square root of 2 can be rewritten as the square root of 16. 16 is a perfect square, so I know that I can just square root it to become 4 as my final answer. Same process for letter B. 6 times 30 is the square root of 120. I'm going to take 120 and break it into 2 smaller pieces. I'm going to find the largest perfect square that goes into 120. Again, I can go refer back to my list. I would probably end up starting about 100 and then working my way backwards until I figured out what works. I'm going to do this in my calculator. And I believe that the largest perfect square we can take out is a 4 out of this. So I'm going to take out a 4. 4 times 30. I believe is the largest we can take out. So a 4 is going to come out. This is radical. This is 2 square root 30. Oh, sorry, not 4 times 30. This is 180. Sorry, I'm trying to do mental math here. I should have a 180 divided by 9. 180 divided by, I'm using my big numbers now, divided by 36. Yes, 36 times 5 here. 36 times 5, 36 is my perfect square. 6 goes to the outside, and a 5 remains on the inside. Sorry about that one. And then the last one here. So now we have some rules we have to take care of. Our rule for when we're multiplying radicals, coefficients, radicands, all that good stuff, is that we're going to take everything on the outside, negative 2 and 3, and that can get multiplied together. And then I'm going to take everything on the inside, 5 and 40, and that can get multiplied together. And in my calculator, 5 times 40 is 200. And now that everything is combined, I can go ahead and simplify what I have left. So negative 6 radical 200 becomes 100 times 2, where 100 is the perfect square. The square root of 100 is 10, so this is negative 60 radical 2. All right, one last problem here. In example 4, we're going to simplify our expression, the square root of 80. David's work is shown below. We're going to figure out what his error is. So if I take a look, he broke 80 into 4 times 20, which is true. 4 was the perfect square that he used. He square rooted 4 to get 2 radical 20. Then he stopped there. His problem is that if we take a look at the final answer that David came to, 20 can still be broken into 4 and 5. So I know that David did not finish. I also know that that means that there was a larger perfect square that David could have used. So if I take 80 and I'm going to go through my perfect square factors, I'm going to list them 1, 4, 9, all the way until I get to about 80. And now I'm past 80. So I'm going to start with 64. 80 divided by 64, divide by 49, divide by 36. I'm going to keep going until I find one that works for me. So the largest one that works. The largest one that ends up working, the square root of 80 can be broken down into 16 times 5. 16 is the perfect square, and we get 4 radical 5 as our final answer. However, if you are doing this in your work and you find that your final answer looks a little bit like David's, that's totally fine, because we can start with something that looks like 2 radical 20, and we can keep breaking that down. So 2 radical 20, like I said earlier, breaks down into 4 and 5, and then we're just going to keep going from here. So if your final answer ends up looking like David's, then no need to worry. We can still end up with the same final answer.